So you can see as the name suggests, so we are going to design and we are going to take care about the what are the different types of design aspects we need to consider, or what is the design procedure we need to consider in the case of design of an 4-bit shifters we need to understand. So generally what you mean by shifter? A shifter is nothing but it is an circuit, it is an digital electronic circuits, so which will shift the given data, so depending upon the direction in which you have designed, so you are going to design that 4-bit shifter either towards the left side or towards the right side. And I told you we are going to use this shift resistors, that is design of 4-bit shift resistors for the multiplication and divisions also. Okay, so how we can make use of these shifters in the multiplication and division? Yes, can anybody tell me how we can make this? Okay, so in the 4-bit shifter, so if we shift the given data towards left side means, as I told you, it will act like a multiplier. So means if I want to multiply by 2 for the digital data, so then I need to shift for the left side direction. Means if I shift the MSB bit now, so it will act like a 4-bit left shifter. Okay, so if I want to do the divider, what I should do? If I want to divide the given digital data by 2 means, so what I should do is I should shift the LSB bit to the right side. So if I shift the LSB to the right side means, then it will act like a divider. Okay, and these shift resistors will play an important role, especially in the case of memory mapping or the design of memory process. Okay, so whatever the design or whatever the shifters you are going to design, so you should make sure that, so here in this case we are mainly talking about a 4-bit shifter. So in this 4-bit shifter, when you want to design the 4-bit shifter, the following things you need to understand. So what is that? The input from a 4-line parallel bus data. So you need to understand. So when any wants to shift the given data, so 4-bit of data, since you are talking about a 4-bit shifters, a 4-bit of data should be parallelly available from the data bus. Okay, and how this parallel data will be fed, or how this parallel data will be received from for the processing, so you need to understand. So means these are the design requirements what you need to consider. Second one, 4 output lines for the shifted data. So when here the 4-bit shifter, we call it as a parallel shifter because you will be getting a 4 bits directly. So because of this 4-bit shifters, so you should have an parallel shifter, that is a data bus which can accommodate the 4 output bits simultaneously. So this is the one more constraints or one more requirement what you need to consider. The next one is the transforming the input data to output lines with any shift from 0 to 3 bits. So when you give a inputs and how we are going to transfer, that is the transformation from input side to output side, so you need to understand from this 4-bit shifter. So these are the prerequisites, or these are the constraints, or these are the considerations what we need to consider when you want to design a 4-bit shifters. Okay, so this is one of the simple diagram what we are going to write for the 4-bit shifters. So you can see here we have a select lines, that is line 0, line 1, line 2, line 3, that we call it as a input lines, and we have a output lines. Okay, so we have a output line. So you can see the input and outputs are created, or it has been designed in a matrix form, and depending upon the connection of these terminals, so depending upon the connection of these terminals, so whether the input will be shifted or not. Okay, so depending upon the switch what we have created over here, so depending upon the application of the switch and the voltage passes across these lines, so you will be getting the output of this 4-bit shifter. Okay, so this is one of the example for 4 cross 4 crossbar switch using a NMOS transistors. Okay, so it will act like a 4-bit shifter. So we will see how it will act like a 4-bit shifter. So this is a basic diagram of a 4-bit shifter. So I request all the students, you please make a note of this. So now you can see how this we can make use of this 4-bit shifter through the use of the buffers. Okay, so this 4-bit shifter, so whatever we have studied, the previous one and this one both are same only, but this shifter we are going to call it as a barrel shifter. Okay, so why it is called as a barrel shifter is because, so here we will be using the buffer at the output sections. So therefore we will be calling this as a barrel shifter. Okay, so the fundamental difference between the normal shifter and barrel shifter is that the processing speed of this barrel shifter will be more when you compare to the normal 4x4 shifter. Okay, so the operation wise it is same only, but in terms of implementation wise the barrel shifter will be changes. So the change in the barrel shifter it has been given in the diagram. Okay, so you can see here instead of the input pins you can see, so we have a input pins also and we have a output pins also. Along with that we have a select line. So with the use of these select lines what happens is, so we can able to interconnect the switches, that is from the buses to the input lines in the form of staircase, that is we call it as a group of fours, and we have a four shift control inputs. Okay, and which are mutually exclusive to each other. Okay, so with the use of this we can able to create a 4x4 barrel shifters. Okay, and one more thing what you need to understand is, so when in the case of CMOS transmission gate, so this CMOS transmission gate can be used for the NMOS pass transistor as a switch in order to provide the improvement in the performances. So this barrel shifter, okay, so the transmission it like a transmission gate. So with the use of this transmission gate, so we can make use as a NMOS pass transistor with as a switch in order to improve the performance of this the 4x4 shift resistors. Should we go for the next one?
Yes, sir.
Yes, sir.
Okay, so this is which is related to your 4-bit barrel shifters. So what as a summary, so what we can mean summarize this. So first you need to find out what are the specifications you have drawn for those design process you need to consider, and how we are going to design the system into subsystem, and how we are going to create a hierarchy of this subsystem so that the overall architecture you can create. And the next one is the tentative floor planning. So what you mean by floor planning is placing of the components before the manufacturing of your entire circuit, we call it as a floor planning. So how the wiring has to be takes place, where the power inputs has to be given, with the output lines has to be there, where exactly the transistor has to be placed in the chip. So all those things you need to make consider. And the next one is you need to determine the interconnections. Okay, so from one system to another subsystem, so how you are going to interconnect, if there is any crossovering happening or not, so how you need to take care of those, and how you can minimize the length of the buses and control lines so that the subsystem can communicate with the memories. Okay, and once you have thorough with this all the connections, or once you are thorough with all the design aspects, then we go for the development of the stick diagram. Okay, so once I design the development of the stick diagram, so then what I will do is I will go for the standard implementation, that is nothing but a mask layout implementation I will be doing. Okay, so these are the different design procedures what you need to understand. So in this design procedures we have studied two important, that is nothing but adders, two 4-bit adders we have studied, and one more we have studied a 4-bit shifter we have studied. Okay, so this is a summary which is related to the design process. Okay, So take down the next one is, so the one more important computational element what we are studying is the design of a 4-bit ALU we will be designing. So in the design of 4-bit ALU, so what are the important things you need to consider has been depicted in diagram. So I request all the students make a note of this diagram. So basically what you mean by ALU is nothing but arithmetic logic unit. So this arithmetic logic unit, especially we are going to use in the case of all the processors or the microcontroller in order to do the basic logical or additional operations. Okay, so you can see the diagram. So this diagram, it depicts the data path flow of a 4-bit microcontroller. Okay, of the 4-bit microprocessor, sorry. Okay, so what are the four essential elements of this implementation of this 4-bit microcontroller? It is nothing but it is a design of your arithmetic logic unit. Okay, and associated with, so this is the fundamental means the 4-bit logic unit, it has to be there. Along with that you need to have some peripheral or a subsystem. So those subsystem, it has been given it over here. Okay, so and one more thing what you need to understand is the fundamental goal of this arithmetic logic unit is to design of the 4-bit adder. Okay, so which is used to perform all the logical operations. The fundamental goal of this arithmetic logic unit, what we are doing is, or what we are designed is, in order to do the all the additional 4-bit additional operations which are associated with, and all the logical operations which are associated to the 4-bit adder we are considering. Okay, and basically what the 4-bit adder will does is it perform the addition of the 4-bit operands and produces the result. So when it produces the result, so we will be having two outputs. So what are those outputs? We will be getting one sum and carry. Okay, so you can see here, as we get the output of this 4-bit adder, so we will be given to the shifters. So based upon the shifters we can take that output and we will perform this to the depending upon the next operations what it has to be undergone. Okay, so now you can see here what happens is, so the output of this 4-bit adder, so we will get the one is a sum and one more is a carry, and these carries we have shifted, or this carry we will be shifting to the 4-bit parallel sum of your ALU. Okay, so we need to add one more important component for this adder, and this component we have been discussed over in this diagram. So what are the various components we have here in this case? You can see here input output ports we have, and 4-bit registers you have, and a 4-bit end around shifters we have. So these are the subsystems what we call it as for the 4-bit ALU. So you can see the input for this 4-bit ALU is nothing but A and B, and whatever the adder we have considered, it is a 4-bit adder. So what we are trying to do is we are making use of Cn as one more input. Okay, so we are making as a Cn as a one more input, and this Cn will be taken from the one more 4-bit registers. Okay, and simultaneously we are giving the input signals, that is A, B and Cn for this 4-bit ALU. And in order to control the operation of this 4-bit ALU, we have given the clock and the control pins. Based upon the signal what we are going to transmit on the control pins, so you are getting the output, that is a sum and carry. Okay, and the output of this sum and carry, since we are storing it in the shift registers, so depending upon the shift control values, or depending upon the shift control signals, the data can be read from this 4-bit ALU subsystem. So how the design of this 4-bit ALU, that is basically we are designing a 4-bit adder. So you can see what are the input terminals we have and what are the output terminal we have. It has been given over here. Okay, so you can see here. So the input terminal A, B, AK, BK and CK is there, and we have output terminal, that is nothing but SK and CK. Okay, and this is a 3-bit adder they have given you. So this they have given you this 3-bit adder in order to just for the understanding, they have given you this 3-bit adder. So if you understand this 3-bit adder, then easily we can go for the 4-bit adder. Okay, so you can see this is a full adder circuit what we have having. So you can see when A is equal to 0, B is equal to 0, C is equal to 0, the output will be 0, 0. When A is equal to 0, B is equal to 1 and C is equal to 0, output will be sum will be 1 and carry will be 0. And your when A is 1, B is 0, C is 0, the output will, sum will be 1 and carry will be 0. Whereas in the case of when A is equal to 1, B is equal to 1 and C is equal to 0, the sum will be 0 and the carry will be 1. Why? Because when you add in binary 1 plus 1, you'll be getting 1 0. So that 0 is nothing but sum and 1 is nothing but carry. So similarly, if you consider for the decimal number, so what you are going to do is when you add 1 plus 9, so you'll be getting 10. Okay, so the same mechanisms we will be using in the case of binary. Since in binary we have only two variables, that is only two values we have, 0 and 1. So if you add 1 plus 1, that is the highest value, so you'll be getting 1 0. So means one increment will be gone, so you'll be getting a 2 power 1 value. Okay, so you'll be getting the input pins, that is the sum you'll be getting and the output you'll be getting. So you can see the output terminal when the input is 1 1 0. So you will be getting sum is equal to 1 and carry is equal to 1. Okay, so this is how they have designed over here. Okay, so for the sum, they have given you this expression that is based upon the sum. So they have come up with a Boolean expression that is nothing but Sk is nothing but Hk and Ck minus 1 bar. Okay, Sk is nothing but Hk in Ck minus 1 bar plus Hk bar into Ck minus 1. See that is tick symbol is there, right? It is basically it is a bar and it is a bar. So this is the output of a half adder and this is the output of a half adder. They have given it over here. Okay, and what about your carry? So carry is nothing but, so this is the AK into BK. It is the output of the first half order, and this is nothing but HK into CK1. It is nothing but the output of this half adder multiplied with your CK minus 1 you will be getting. So therefore you will be getting this as a carry and this as a sum. Okay, so whereas the half adder output, you know that what is that half adder output, that is nothing but H is nothing but it is A bar B plus A B bar, A bar B plus A B bar, A B bar. Okay, so therefore they have written like this. So this tick is nothing but it is a bar only, so you need to write it over here. Are you able to understanding what we are discussing? Yes. Okay, so this is how we are going to design an full ladder. Okay, so for now what we need to do is we need to design a adder element, or we call it as a basic element or a fundamental element we need to add. So for that what we need to do is, so we need to consider a adder element. So each bit adder element we need to consider. So if you already studied this thing, you already studied. So if you remember the logic design, okay, so what is this logic design is, so you'll be getting AK into BK, and depending upon the carry in value, so you'll be getting the sum value. Okay, and when you add this, so depending upon the carry in, you'll be getting a C out value that we call it as a CK, that is CK, and this is CK minus 1, the previous carry and the new generated carry, you need to highlight it over here. Okay, so therefore what they have given is, so you can see in this expression, the adder requirement may be stated as, so if AK is equal to BK, then what will be your SK will be CK minus 1, or else what happens is, you can see here SK is nothing but, that is sum is nothing but CK minus 1. So how? So you can see over here. Okay, so you can see over here, once again you read it, when AK is equal to BK, the sum is equal to the previous carry. Sum is equal to the previous carry. Okay, you can see here, when A is equal to 1 and B is equal to 1. So this condition. So when A is equal to 1 and B is equal to 1. So this is the condition what you can getting. So you can see here, your sum will be the previous value. So therefore you are getting CK is equal to 1. Therefore you are getting Ck is equal to 1. Okay, so you can see what is the previous case. You have this carry is equal to 0, so therefore you are getting sum is equal to here. So now you consider the previous case, one more condition. So here, when a is equal to 0, b is equal to 0, what will be your sum? Sum will be the previous value. Sum will be the previous ck. Sum will be the previous ck. Okay, this condition also you can see when a is equal to 1 and b is equal to 1. So what is the sum? Sum is nothing but the previous value. So previous ck is this one. So previous ck is this. Okay, so therefore we have written the expression like this, or else what happens is your sk will be ck minus bar. Your sk will be, that is sum will be ck minus bar. Okay, and for the carry you can get an expression like this. So what is that expression? When ak is equal to bk, what will be your ck? Your ck is nothing but which is equal to ak and bk. If that is the not case, means then what will be your newly generated carry will be your ck minus 1. So based upon this relationship, we can able to create an adder element. So what is the adder element? It is nothing but input terminals, and you'll be having a carry in, and you'll be getting the two output terminal, that is nothing but a sum and output. So based upon these identities, or based upon these identities, we have generated this adder. I have scheduled the VLSI quiz for you. Okay, I think it starts from 9:30 to 9:55 will be there. So I request all the students kindly take up the quiz. Yes, Abhishek, Jayavardhan, Rupashree, Deepshi, please take down the quiz. VLSI quiz I scheduled. Have you got the notification?